So in this video we're going to do a bit of physics, in particular Newtonian dynamics, and we're going to derive the trajectory equation. So this is the problem that we're going to ask. We're going to consider a ball, something that we can model as a point particle, and it's going to be projected up off the ground, the surface of the Earth here, at some angle which we'll call alpha, and at some speed which we will call v. And we want to know what path is this ball going to follow. That's what the trajectory equation is going to be. It's going to be an equation for the path that this particle will follow. And we can then ask questions like how far is it going to get by the time it's landed? How long will it be in the air for? What's the time of flight? And we can also ask what's the maximum height that it will get to. Assumptions that we're going to make, we're going to disregard air resistance, and we're going to make the assumptions that we make all the time in physics, that time can be modelled as the real numbers, and that space can be modelled as r3, or actually in this case we're only going to need 2 dimensions because we can look at from the correct angle, and indeed the particle is going to move within one plane, so as long as we look at the correct angle then we don't need to worry about the 3rd dimension. So we're going to start by putting a coordinate system onto our space. So as I've said previously, as long as we view the problem from a good position, then we only need to actually put a coordinate system on 2 dimensions of space because the particle is going to move in a plane. So that's what we'll do. So we will call the horizontal displacement x, and we'll center 0 at the starting place on the center of the Earth where the ball is being projected up from. And then we'll have our vertical displacement, we'll call that the z-axis, and we'll center that again so that 0 is at the place where the ball is starting, i.e. 0 is the level of the surface of the Earth. And we will make this coordinate system so that the units all work. So 1, in a displacement of 1, let's say along the x-axis, we'll make sure that this coordinate system is attached to space properly, so that that actually is 1 meter displacement. So you'll put the numbers at the correct places to make the units all work out. And we're going to use the gravitational acceleration constant, little g, which is approximately 9.81 meters per second squared. So it's important, therefore, that our coordinate system is properly put onto our space when we're doing the maths, so that we can actually use this number. If, for instance, we didn't put the coordinate system on properly and, moving 1 displacement along the coordinate system actually was, 3/10 of a meter displacement, then this constant wouldn't work. All of the equations that we're about to do wouldn't quite work with this constant. So you need the coordinate system to be put on space correctly. And really what we're just doing is ascribing to every point in the 2-dimensional space here a pair of real numbers, a element of the abstract mathematical structure that is R2. And of course, that abstract mathematical structure has all sorts of incredible properties defined on it. It has addition of vectors, scalar multiplication of vectors, calculus, for goodness sake, defined on it. If we have, for instance, a function from the real line into R2, we can do calculus on that, and that's what we're going to view our trajectory as being, a function from time, which we'll model as the real numbers, into space, which we're modelling as R2, and then we can do calculus on that function from R to R2, and we can infer incredible things about reality from our abstract mathematical structure that's modelling it. And that's really incredible because of the fact that these mathematical structures are capturing the same patterns that are inherent in reality. They're capturing the same patterns that are inherent in time and in space. So let's set to work then now. So we have our particle here. We'll say it has mass little m. Of course, little m is going to vanish very quickly because it will cancel out with F is equal to ma and the gravitational force. So that won't be in the problem for very long. But we'll say we have our particle. It's got mass little m, and it is starting the situation moving in this direction. So angle alpha, up at a speed v, and again v is in the correct units, so meters per second, to make all of this work. And once it's gone, the only force that's going to be acting on it is gravity. So of course, to get it, to actually project it into the air, you would have to exert a force on it, but we're assuming that bit's already done, and now it's moving in this direction at that speed v. After that point, the only force that's going to act on it, that's going to change its motion, is going to be gravity. So here's the equation for the force of gravity. So force is going to be a vector quantity, so I put the line underneath it to denote that it's a vector, and basic gravity law on the surface of the Earth is that the gravitational force anything feels is just its mass times this constant little g, 9.81. So this is the size of the gravitational force, and it's going straight downwards, so we're going to use k with a line underneath it to mean the unit vector upwards in the direction of z, and we'll use I to be the unit vector in the direction of the x-axis. So the force is therefore going to be minus, because it's going to be pointing downwards, mg in the direction of k. Now what we really want to find is the position vector r, so the position of the particle, and we want to find it as a function of time. How are we going to do that? Well, we need to get r from acceleration. So the position vector, if you differentiate that, you get the velocity vector, and remember v is a speed rather than velocity, but if you differentiate the r vector, you get the velocity vector, and if you differentiate the velocity vector, you then get the acceleration vector, and we can get the acceleration vector using Newton's second law, which says that the force vector is equal to the mass times the acceleration vector, or rather, that if you know the force vector that a particle is experiencing at any time, then the acceleration vector is just going to be equal to that force vector divided by the mass. So mass times the acceleration then is going to equal this thing that we've got as the force vector, and that is Newton's second law. So now dividing both sides by the mass of the particle, little m, and we get that the acceleration vector is just going to be equal to negative g, this constant, in the k direction, so g pointing downwards like that. Now to get the velocity vector, you need to integrate the acceleration vector, so anti-differentiate. So anti-differentiating this with respect to time fundamentally is how you go from the acceleration to the velocity. It's the integral of this with respect to time. So this is just a constant with respect to time. There's no time variable in this expression at all. So when you integrate a constant, you get that constant multiplied by the variable. So we're just going to get minus g times time now, multiplied by k. But of course, this function alone isn't the only thing that would differentiate with respect to time to give this. No, instead what you could have had is constant terms, and you could have had constant terms in any of the three directions. So you could have had a constant term in the k direction that when you differentiated with respect to time would have vanished. You could have had a constant term in the I direction, and even the j direction, which we haven't even defined, which is going into the board. So really what we've got is a constant vector here, because it's a constant in each of the three directions. This is basic vector calculus, that if you've got a function from some real variable, which is what time is being modelled as, into a vector space such as R2 or R3, then if you want to differentiate that function with respect to time, it's just the derivative. It's just a vector, and you just differentiate each component of the vector with respect to time, and then that new vector that has the derivative of each of the components in the equivalent places with I and j, that's the derivative. And equally with integrating a vector function of a real variable, you just integrate each of the three components separately. So that's what we've done here. We've just integrated each of the three separate components. And now what I've put here is plus this constant of integration, which is now a vector, because it's, if you like, it's c1 in the I direction plus c2 in the j direction plus c3 in the k direction, but that in itself is a little vector, and we could just bunch it together as just a constant vector. Now, how are we going to work out what that needs to be? Well, we're going to do it from the original starting velocity, because we know when time is equal to 0, and we might as well, we have the freedom to define, where we're inputting our coordinate system, if you like, for time. So we might as well define t is equal to 0 to be the start of the problem where the ball is just moving off the ground. So we can put t is equal to 0 here, and the answer at the moment would be that v, this vector, is going to be equal to 0 therefore, but that's not right. We need it to be equal to this vector going upwards with magnitude v that we had earlier. So let's do that now. So if we look at what the velocity vector was at time 0, we could call this v with a line underneath it because it's a vector at 0 to mean at time 0. This is just going to be equal to this. So v without a line underneath it means the actual speed that it was going originally, so the modulus of this, if you like. And then we want the two components. It's got a component in the I direction and a component in the Z direction. I've just realized I've made a mistake here, so let me just alter that. So that's better. It's got a component in the Z direction, and the size of the component in the I direction is just going to be the modulus of the vector times cosine of this angle. That will give this side of the triangle. So we'll have v cos alpha in the direction of I, and then this bit here is then v sine alpha, the length of this side of the triangle, in the direction of k. So that is the starting vector, velocity vector for the particle. So actually, this function for velocity as a function of time, it needs to be correct at t is equal to 0, and at the moment it's not. If you put in t is equal to 0 here, you get the 0 vector. So this has to go here as this constant of integration, because of course if you integrate, if we stick this on the end here, if you integrate this doesn't depend on time at all. These are just constants, so they vanish away. So it's still, sorry, if you differentiate this, so if you put this in here and then differentiate this expression, this bit differentiates away because it's just constant, so it will go, and you'll just end up with the derivative of this, which is negative g in the direction of k, so you'll get back to the acceleration, correct acceleration vector. So this is the bit that you need to put in here to make this expression correct, given our starting requirements. So what we can then do is just collect together the terms that are in the same direction. So here is v cos alpha in the I direction, so just a constant in the I direction, plus, and then we've collected this term and this term together because they're in the same direction. So we've got v sine alpha minus gt in the k direction, and that then is our velocity vector. And just to emphasize again, v without a line underneath it means that speed, that initial speed in that, at that angle alpha, and v with a line underneath it means the actual velocity vector as a function of time. So now, more basic Newtonian mechanics. We want to go from this to the actual position vector. Well, the velocity vector is the time derivative of the position vector, so to get the position vector from the velocity vector, we just integrate with respect to time, and again we'll get a whole general solution with a constant of integration, and then we'll just have to pick the one that satisfies our initial conditions, that at t equals 0, its position is 0, 0, and there will only be one solution to that. Just like in this case, this gave a whole class of solutions that all satisfied the property that their time derivative was equal to this, but there's only one that then satisfies that property and also the property that at t is equal to 0, its velocity is equal to this, and that's what we've got here. So anti-differentiating this then yields what we have here. So remember again, this might look complicated, but this is just a constant. We're given these things, v and alpha, initially. They are our starting parts of the problem. So this is just some number, some real number. So it's not scary. So when we integrate that with respect to time, it just becomes that times time. I've put time in this position. The reason being is if that I put it after the cos of alpha, there's a temptation to then wonder whether that's inside the cosine, and of course it's not, it's just multiplied by cos of alpha, which is why I've written it like that instead. Same here. So we're now anti-differentiating this with respect to time, and again we're doing it component-wise because that's the way vector calculus works, thankfully. So anti-differentiating this with respect to time, again this is just some constant term, so that's just going to become it times time, so vt sine alpha. And then this this is a bit more interesting. So we've actually got a linear term in t, so anti-differentiating that yields t squared over 2, so raise the power and divide through by the new power. So we've now got minus gt squared over 2. And again, we've got a whole class of solutions because we have the constant of integration, and anything of this form, where this is some constant vector, will satisfy the fact that when you differentiate it with respect to time, you end up with this velocity vector. So we now just want to find the single solution that satisfies that at t is equal to 0, the position vector is the 0 vector. So stick in t is equal to 0 into here, that goes to 0, and this also goes to 0. So actually it's correct without any constant terms. We actually just want to make that equal to the 0 vector, so get rid of it. If you made it anything other than the 0 vector, it wouldn't satisfy our initial condition that at t is equal to 0, the position is 0i plus 0k. So here we go then. This is actually an equation that tells you the position vector as a function of time. So it tells you at any time, you give me any time, and I will tell you what the position vector is going to be. This is what the x value will be, and this is what the z value will be. Now, of course, at some point it will become inaccurate because it will follow the trajectory of the particle as it goes up, up, down, down, but then it won't stop when it hits the Earth again. It will just continue going on and on because there's nothing in these equations that stopped it from, that made it stop once it came down to the value z is equal to 0, so it will continue on. This is not actually the trajectory equation. The trajectory equation comes from eliminating time out of here. So we would like to actually know what is the function that describes the actual path that it's going to follow. So if we drew the trajectory it's actually following, it will be a nice line, and we'd like the equation of that graph, so we'd like z as a function of x. So that's what we're going to get from this now, and that function, z as a function of x, the actual equation for the line that the ball is going to follow, the trajectory that the ball is going to follow in this projectile motion, that's what is called the trajectory equation. So the way we do this is quite simple as follows. So we note from our equation here that the x value at any time is just equal to this bit, so vt cos alpha. So you give me any t value from 0 onwards, although actually it goes for the negative numbers as well. It's not particularly relevant to the problem that we've actually asked about. But you give me any t value from 0 onwards, and then I can tell you what the x value is. I can tell you what the x value is for all of this bit, and of course it continues on for the ball having gone below the surface of the Earth, again because there's nothing in the maths that stopped it from doing that. But we can cope with that. We can just eliminate those irrelevant parts of the graph from our understanding of it, and just use the bit that is actually relevant to the real problem. So you give me any time value and I can tell you what x coordinates the ball will be at. That means that I can invert this to get for a certain x value what the time value is. And this is really simple because it's just a linear relationship. So I just divide through by v cos of alpha, and I get that time is equal to x divided by v cos alpha. So you give me an x value, so I might take this x value here. I can tell you at what time the ball will have obtained that x value. And now what I can do is just take this value, which is the z value at any time, and say, well, now I know what the time is in terms of the x value, so I can plug this into here, and I can get for what each x value what the z value is going to be, and then I'll have a function for what z is in terms of x. So just plugging this in then, so we've taken this, z is equal to this thing, and now we're replacing t with this. So this first bit becomes v sine alpha, those are the bits that stay, and now it's times this, so times the x, and then divided by v cos of alpha. So that's what we get from this bit. And then this bit, damn, we've got a squared term, but we can cope with this. So minus g over 2, and now it's times t squared, which is this thing. So times all of that squared, and let's simplify this now. So simplifying this bit, the v's cancel, then we've got x times sine of alpha over cos of alpha. Well, there is a name for what sine of alpha divided by cos of alpha is. That's tan of alpha. So this bit becomes x times tan of alpha. And then this bit, we've got minus g times the thing in the numerator here, which is going to be x squared. And then all of this goes into the denominator here because we've got this, divide by this, and then divide by 2, which is the same as dividing by 2 times that thing. So we've got 2 times this thing squared, which is just v squared times cos of alpha squared, so cos squared alpha. So this thing that we've got here, which has the z value, i.e. the vertical displacement, as a function of the x displacement, this now tells you, given an x value, what the z value is going to be. This is the equation of the line that the particle is going to follow. This is the trajectory equation, which the whole video is the subject of. So we could put a box around this and label this the trajectory equation. So what we now want to do is try to actually understand this, think about what this means. What does this actually look like as a graph? Because that's going to be fantastic. That's going to tell us what path the particle is actually going to follow. And I should say something very important that I don't know whether I emphasized enough at the beginning of the video. When we did this step here, or actually even before that, when we did this step where we said the only force acting on it is equal to gravity going downwards, we made a massive assumption there. We ruled out air resistance, we ruled out the wind, more importantly we ruled out air resistance. So this trajectory equation gives the path that the ball will follow if you exclude air resistance. In the perfect world where there's no air resistance, this is the path that this ball would follow. Of course, we don't live in that world. We have air resistance. The problem is that when you actually try and put in air resistance into these equations and add a term onto this force equation for what the force actually acting on the particle is with air resistance there, and the equations then become much more difficult. The differential equations become much more difficult. They no longer have perfect analytic calculus solutions anymore. So when you take away air resistance, calculus works perfectly and tells you exactly what path the ball is going to follow. When you put in air resistance, calculus doesn't handle it. No one knows how to get the perfect solution. And instead what we have to do is build numerical approximations for the path that the ball will follow. So we did make that assumption. We excluded air resistance. So this equation gives the path the ball will follow in this perfect world where there's no air resistance acting on it. Anyway, back to understanding what this function looks like. So remember, it gives z as a function of x. And all of these other bits that look so complicated, the v squared, the cos squared alpha, the g, the tan of alpha, these are all just numbers. So all it is some number times x squared, notably negative that number times x squared, plus some number times x. So this is a quadratic function, a negative quadratic function. So it's an upside down parabola. So I've drawn that here. So this is what it's going to actually look like, an upside down parabola, and it will continue on down here and it will continue on down here because there was nothing in the maths that said that it needed to stop there and there. We can handle that because we will just restrict our attention to this bit, which is the bit that is actually relevant to the physical problem. Now, we want to think about where is it going to cross the x-axis. So to do that, we can think about setting this equal to 0 and finding the two x values that are the solution to that. So because there's no constant term in this quadratic formula, we can factor an x out instantly, and that's the solution that x is equal to 0, which we knew. That's one of the points where this parabola is going to cross the x-axis. And then the solution to this other one here, this factor, the x pulled out, so we've pulled the x out here and we've got tan of alpha minus gx over 2v squared cos of alpha. We can rearrange that to find what x is equal to, and that solution will be here where the ball actually hits the surface of the earth, and that will tell us the x value, the x displacement, how far this ball is going to get, the range of the ball in this projectile motion. So this is going to be equal to 0 either when this is equal to 0 or when this is equal to 0. So when this is equal to 0, that's that solution. Now let's find when this is equal to 0. So this thing needs to equal 0. Just rearranging this, bring this onto this side, and then cross multiply. So you get that x is going to have to equal 2v squared that has come up from the cross multiplication times the cos squared alpha times tan alpha, and then all divided by the g that was here. So this is the x value that will make this equal to 0, i.e. one of the solutions to this thing equaling 0, i.e. this solution over here where the negative parabola is crossing the x-axis. Now just doing a little bit of trig manipulation here. So tan of alpha, remember, is sine of alpha divided by cos of alpha, so that cos of alpha in the denominator cancels with one of the cos of alphas here, so you get that this is v squared over g times 2 sine of alpha cos of alpha, and then we're using finally a trigonometric identity which says that sine of 2 times alpha, so sine of double the angle alpha, is equal to 2 times sine of alpha cos of alpha. That's a famous trigonometric identity. It comes from the formula that sine of a plus b, where a and b are two angles, is equal to sine of a cos of b plus cos of a sine of b. And then, of course, when a and b are equal to one another, that would give the scenario of sine 2a, and that just gives 2 sine a cos a. So overall, this then is the answer for the other x value where the z displacement is going to be equal to 0, and this is the range of the projectile. It's how far the ball is actually going to get, because of course we don't care about this bit and we don't care about this bit. So we often, when we're studying the trajectory equation, we often denote this little d. So this is called the range of the projectile. It's denoted little d, and it's equal to v squared over g sine 2 alpha. So given the starting conditions, you knew what alpha was, you knew what v was, that's just the speed. You can work out how far the ball is actually going to go, as long as we're excluding air resistance, of course. Everything we've done in this video excludes air resistance. So now what we're going to do is we're just going to work out two more things. We're going to work out the maximum height that the ball is going to get to, and we're also going to work out the time that the ball is going to be in the air, the time of flight. So let's first try and work out the maximum height obtained by the ball, which we'll call little h subscript max. So to do this, we can think about parabolae. So remember, the motion is going to be parabolic, starting at 0 here and getting to this horizontal range here. And parabolae are symmetric. So there's going to be a line of symmetry down here, with this side completely symmetric to this side, and the maximum height that this parabola is going to obtain will be right in the middle. Because these two are at the same height, we know that the line of symmetry has to be between those two, so it has to be right down the middle here, and that's the point that the parabola is going to be at the negative parabola is going to be at its maximum. So all we need to do is take this, divide it by 2 to get that point, that x displacement that's in the middle there, and that's the x value that the z value is going to be at its maximum, i.e. the maximum height. So we just need to plug that into the trajectory equation to get what that z value is equal to. So that's what we'll do now. So I've copied the trajectory equation down here because it's difficult to remember, and what we now want to do is take this thing, divide it by 2 and plug it in for the x value, and that is going to give us our h max value. Now for this, because we're going to have to do a lot of trigonometric manipulation again, it's actually helpful to rewrite sine of 2 alpha back as 2 sine of alpha cos of alpha, and then note that when we divide that by 2, the 2 is going to cancel, so it's going to be v squared over g times sine of alpha cos of alpha. So this thing is equal to that x value that's halfway between 0 and this. So putting this in then, here it is in place of x here, and then we've got times tan of alpha, and you can see that we're going to get some nice cancellation here. So for instance, the cos of alpha is going to cancel with the cos of alpha here, because tan of alpha is sine of alpha over cos of alpha. And then we've got minus g, and then the same thing put in here, so v squared over g, sine of alpha, cos of alpha, all of that squared, and then it's all divided by this bit, which is 2v squared cos squared alpha. So let's now do some manipulation, starting with cancelling those coses. So tidying this up then, so cancelling that cos of alpha then, we end up with v squared over g times sine squared of alpha. Then the more difficult bit, tidying this up. So this thing squared is going to give us v to the power of 4, but then that's going to cancel with the v squared to yield just v squared. And then we're going to get over g squared, but that g squared is going to cancel with this g to just yield over g. The 2 comes from this bit here. Then we've got sine squared alpha times cos squared alpha. The cos squared alpha cancels with this cos squared alpha, so you just end up with the sine squared alpha here. So we've now got this thing minus this thing, and this thing, note, is just a half times this thing. So you've got this times the half of it, so you just end up with a half of this. So v squared over 2g times sine squared alpha, that is the maximum height that this ball is going to reach in this projectile motion. The final thing we want to work out is the total time of flight, so the time from setting off to the time that it lands back on the surface of the Earth. So to do that, all we need to remember is that we had this relationship between x and time. So x was equal to vt cos of alpha, and indeed time was equal to the x value divided by v cos of alpha. So given any x value, we can find what time the ball reaches that x value. So now all we need to do is put in x is equal to the range of our projectile, that final value that it gets to when it hits the surface of the Earth. So that's what we'll do now. So here we go. So I've copied this formula, t is equal to x over v cos of alpha, down here. Here is the formula for that final range, the final x displacement that you get to when the ball hits back z is equal to 0, the surface of the Earth. So we just need to put this in for x here. So again, I've changed the sine to alpha back into 2 sine of alpha cos of alpha, so v squared over g, 2 sine of alpha cos of alpha, and then we want to divide this by v times cos of alpha. So the v squared is going to cancel with the v to just yield 1v, the 2 is going to remain there, so we've got 2v over g, which comes from here, and then the cos alphas cancel, and we just end up with sine of alpha. So time of flight until you reach the surface of the Earth again is given by this formula here. T is equal to 2v over g times sine of alpha. Again, just in terms of the initial speed, the initial angle of projection, and the gravitational acceleration on the surface of the Earth. So what we've now done is we've found the trajectory equation, and we've found 3 important values associated with this projectile motion, namely how far the ball is going to get, what's the maximum height it obtains, and how long is it going to be in the air for. And remember, everything we have done is excluding air resistance. This is how balls would move on the surface of the Earth if there was no air resistance. And unfortunately, whilst calculus works perfectly in this scenario and gives us perfect, beautiful analytic solutions, as soon as you put air resistance and try and do the equivalent thing, the differential equations you get become unsolvable by analytic methods. They have to have numerical approximations, and we have to use computers to make them better and better and better, and therefore we can get very good ideas, very good predictions of the paths of the motion by using computers to get closer and closer until, frankly, it's as good as perfect, but it's not as satisfying in terms of being able to do it with paper and pencil as we have here. So thank you for watching this video. I hope you've enjoyed it and learned something.